Hello and welcome to day 5 of Solution1. My name is Clinton Ingram. You can call me Clint or Sauce Control, my handle on the C# community Discord and on GitHub. I am filling in this session this morning for a late cancellation. I think the original topic was something to do with ASP.NET, but we just finalized this session on Saturday afternoon, so I haven't had a lot of time to put this together, but hopefully I've got some interesting content for I tried to tackle kind of some beginner stuff just in case you haven't set up BenchmarkDotNet before. I'll show you how easy it is to get started with it. But I'm also going to spend a lot of time talking about pitfalls and tricks around BenchmarkDotNet. So a little bit of advanced content too. I've been working with C# ever since actually the betas of .NET 1.0, and I love the language from the beginning, but I've also had a passion for performance-oriented programming. And for the longest time, we had to drop out to C for some of those really core performance bits and then call them from C#. But ever since .NET Core came out, we've had better and better tools and better JIT and better and better base class libraries, such that it is really easy now to get high performance out of pure C# code. And part of, I think, the performance environment around C# includes tools like BenchmarkDotNet, like SharpLab. These tools make it easier to explore performance and to understand why things perform the way they do. But I think if there's one overarching theme for the talk I wanted to give today, it's that while benchmarking benchmarks are a valuable and powerful tool for discovering the performance characteristics of code, either your code or other code that you're using, they are not a substitute for understanding how things work. And the reason I say that is a lot of times we see poorly designed or poorly implemented benchmarks that give real numbers that we might be tricked into believing are real and meaningful, but because they're asking the wrong question or asking the question in the wrong way, they're getting the wrong answer, and that can lead people to wrong conclusions and wrong decisions and wrong actions. So we want to try to avoid that. So I want to talk a bit about best practices for benchmark design. I'm going to hit a bit about how BenchmarkDotNet works, because understanding how it works will give you a bit more ability to interpret its results correctly. And then again, I'll show you some pitfalls, some holes you might fall into, and tricks to avoid those things. I, again, will apologize for the lack of preparation here. I don't have any slides. I do just have a couple of demos here, and then I've set up some examples in SharpLab so we can look at some stuff. But I'm going to jump right in with this first sample project. And this is a benchmark program that I wrote not using BenchmarkDotNet. And the only reason I'm not using BenchmarkDotNet is just so I can show you how easy it is to set it up if you haven't used it before. But the purpose of this benchmark program, ostensibly, is to measure the difference in performance, difference in speed between iterating over a span of int using a for each loop versus a for loop. Now, a lot of you will probably already know that this is a silly question because they're the same, but I've seen benchmarks like this. You may have seen benchmarks like this. It's asking a question that maybe a benchmark isn't the right tool to answer, but the way I've set it up is at least not terrible. It's not the worst benchmark I've ever seen. So I want to talk about first what's good or reasonable about it. I'll just preface this bit by saying that I have structured this benchmark program in a way that will make it really easy to integrate BenchmarkDotNet. So it may look a little bit weird, but mostly normal, I would say. So this is a new style C# program with a invisible main method. So I just got this extra class in here called iterate_span. It's got a count on it, which is being used in these two test methods so that I can control the number of elements in the span that I'm passing to it, or that it's retrieving. And if we look at the contents of each of these methods, all they're doing is they're calling this data class that's off to the side that returns a span of a certain length. And they're both doing that in exactly the same way. So they're getting the same data. They're both setting up this accumulator value and then looping over the items in the span, XORing that value into the accumulator and then returning the accumulator. Now, I want to take just a minute to talk about this XOR business. It doesn't matter that it's an XOR that I'm doing, but what is important about this is two things. One is that we are making sure that we're doing some work with the values as we fetch them out of the span. And I want to show you why that's important. I've got a SharpLab example set up over here. And the first loop that I've got here, let me zoom this, I guess. Oops, there we go. The first example I have over here looks just like the one in the benchmark. It's enumerating over a span, accumulating with XOR into this accumulator and then returning it. And the second example here I have is looping over the span. It's retrieving the values from the span. Oops. But it's just putting them into a variable and then not using it in any way. And then the third one here just loops from 0 to the length of the span, doesn't even bother trying to read from the span. And I've actually seen people write benchmarks like this where they're trying to measure iterating over something and they just write the for loop, but then they never actually fetch the items inside. And I want to show you the disassembly for these two methods. It doesn't matter if you don't read assembly language. The important thing to note here is that the bottom two, the one where I've retrieved but ignored the value from the span, and the one where I just looped over the count, these two have the same generated assembly code. There's one subtle difference between them, which is that the order of the first two instructions is different. We have move XOR versus XOR move. This XOR has nothing to do with the one in the code. I guess I should have picked a different instruction, but anyway, the top one here where we're actually using the span value and XORing it, that's this line of XOR right here. This is the body of my loop. And it is fetching the value from the span and then XORing it. It's only one instruction, which is good because that means that this work is not overwhelming the overhead of the loop that I'm trying to measure, but it is doing something. And by doing something, we ensure that the code is actually run, that we are actually retrieving the values from the span. Now, it's kind of interesting to see how the JIT compiler optimized this. Again, we saw that fetching the value was not enough to actually do the work. The JIT can see, I see you reading the value, but you're not doing anything, and reading it doesn't have any side effects. So that's a perfectly fair optimization just to throw out that read. And that's what it's doing. If we were to look at an optimizing C++ compiler, it might go even further. And in fact, I've done that here. I've translated my bad method to C++ using a standard span, which is basically the equivalent. I'm looping from 0 to span.size, and I'm fetching the item into a variable, but not using it. And sorry, I should have zoomed that as well. So here it is in C++. And then on the right-hand side here, I've got the compiled assembly from two optimizing C++ compilers, GCC 12 and Clang 14. And look at this, they both optimized this method down to just a single return instruction. So it's seeing, I'm literally doing no useful work here. This method is gone. Just throw the whole thing away. And if I were to add in an accumulator, oops, and then actually just use it, you'll notice it's still throwing it away. So I'm reading the value, I'm doing something to it, and yet still the compiler's just optimizing this whole thing away. And the reason is I'm not returning anything. So even though I'm accumulating into this X variable, that's still busy work because no one will ever see that result. So finally, if I change the return type of this and return X, now we get some actual code. This is some fancy auto-vectorized code from our optimizing C++ compilers. So it doesn't look the same as what we get from the JIT. But the point is that it's a fair optimization to throw out any work that doesn't have observable side effects. And so we want to make sure in designing a benchmark that that we're actually doing some work that cannot be optimized away. And so that's why I'm doing something with the values, and that's why I'm returning them. Now, there's another reason that it's good to return this value, and that is that realistically, I want to make sure that each of these methods is doing the exact same thing. And this return value, because it's using the same data and calculated the same way, should be the same for both of these methods. If it's not, then that means I screwed something up. And then it doesn't matter which one is faster because one of them is wrong. So we want to make sure we're getting the right answer. And this just serves as kind of a dummy check to make sure I haven't screwed something up. The last thing I've got in this method in this class is a static method called run benchmarks. And this is not good, by the way, but it's also not the worst I've ever seen. I am starting up a stopwatch. I'm running each method, stopping the stopwatch, and then just fetching the elapsed ticks. The stopwatch has a variable increment depending on your system. On my system, a tick is about 100 nanoseconds. It could be more, it could be less. It doesn't really matter. I'm really just trying to compare the relative performance of this, so it doesn't matter whether it's 100 nanoseconds or 500 nanoseconds. I'm just getting the number. And then I'm also I'm fetching the return value of each of these methods, the dummy check value, and I'm dumping that out. And if I were to run this, here's the result. I see that the two check values are the same, so I'm doing the same work. But I see that the for each loop took way longer than the for loop, and that's what makes this a really bad benchmark. Is I've only run each method one time, and when I ran the first one, that was the first time we actually tried to gather the data. And that means that the data was probably constructed at the time that I ran that first method. So it was unfairly penalized. And each of the methods had to be JITted. In the tiered JIT environment, which we have in modern .NET, they would have been JITted to an unoptimized version of the code. So there's really nothing accurate or representative about the results that I've got here. And BenchmarkDotNet is designed to deal with those problems and a whole bunch of other problems you haven't thought of, but that are important to getting accurate benchmark results. So again, my main method here is just calling that run benchmarks static method on my benchmark class. So let's BenchmarkDotNet this thing up. I'm just going to drop out to the command line and do a .NET add package benchmark.net. I'm going to type very little in this presentation because I am poor at typing. So there we go, we've added it, and then because I'm going to pop back over to Visual Studio right away, I'm going to do a .NET restore, just make sure everything's all set. So now back in my project, the only thing I need to do to BenchmarkDotNetify this benchmark program is I need to add a job attribute. And BenchmarkDotNet, in BenchmarkDotNet, the job is the kind of the outermost configuration that you have. It controls building your benchmark program, launching the benchmark program, and then how many times your benchmark program is run, what runtime it's run in, all that kind of stuff. The simplest job is aptly named simple job. And I'll rely on IntelliSense to fill in the namespace for me, or not. So I just need a using benchmark.net.attributes is where these attributes live. So the simple job, again, is the simplest job. It's probably the one you want to use. It's as a good default. And then for each benchmark method that I want to benchmark, look at this. It's automatically suggesting I apply the benchmark attribute to these. So boom, benchmark attribute. And that's it. That's all I need to benchmarkify this, this test class that I have. The last thing I need to do is actually run the benchmark. And for that, we're going to use the benchmark runner dot run, and it's got a generic overload of it. And you just pass in the name of the type that contains your benchmarks. And that's going to run our benchmarks. One thing I like to do, since I've already got this method here, and since it is doing something useful, it's dumping that dummy check so that I can make sure that the work done is the same. I like to just kind of leave that there, and I might just throw this behind a, actually, let's dump out a prompt. So we'll do a console.write. We'll say press B to benchmark, any other key to exit, like such. And then we'll say if console.readKey .keychar equal B, then we'll run the benchmark. Otherwise, we will go ahead and allow the program to exit. So that's kind of a standard setup that I might use. And since this is our first benchmark, I do want to go ahead and run it. I'm not going to run most of the benchmarks here because running benchmarks accurately takes a long time. So we don't want to do that. And it taxes my machine, spins up my fans, maybe messes with my camera and my audio. Hopefully, I'm not going to lose any audio here or anything, but I'll hit B to benchmark. Oh, look what it's telling me here. This is a mistake that I made the first time I ran my standalone benchmark program, which was that I ran a debug configuration build of it. And in .NET, a debug configuration build, when the compiler generates your assembly, it fails to set an optimized flag in there. And then when the JIT compiles your code, it intentionally skips optimizing it in order to make it easier to debug. So BenchmarkDotNet will actually refuse to run your program if it's in a debug configuration. So let's change that to release and run it. And now we get just a whole bunch of spew. I'm going to let this settle down in case my audio is not working. There we go. So the most taxing part of this benchmark setup is actually building your benchmark projects. So it does that in parallel, so that would have put more strain on my system than running the actual benchmark. But you see a lot of spew go by here, and basically it is telling you everything that BenchmarkDotNet is doing. I think a lot of people are they're anxious to see the results, so they'll ignore all of the stuff that's going by, but there's some really good information in there, and we're going to look through that in a minute while talking about how BenchmarkDotNet works, because it helps you understand what the result was that you got. And this will be over shortly. Should get to 15 executions. There we go. So here's our results for this one. It says the for each loop took 417 microseconds and the for loop took 401 microseconds. Now wait just a minute. I said earlier that those were the same, and yet it clearly says here that the for loop is faster. So that's an odd thing for it to say. I want to talk real quick about this error column, because a lot of times we focus on the mean column, which is just the average time that each of the methods took. This error column, though, is really important because what it represents, and it says this right here in the legend that's printed out with the results table, that this is half of the 99.9% confidence interval. Now, if you don't remember any of your statistics classes or never took one, the confidence interval is a range of values where you can expect 99.9% of valid values to fall within this range. And so the error value represents half of that. I actually like the result that it dumps out here. It dumps out a bunch of statistics for your result. Let me zoom in on that just a little bit. So among these statistics that it dumps is the confidence interval. And what it's telling me is for the second method, the for method, the confidence interval was 396 microseconds to 406 microseconds. So we're expecting that that individual test values should fall within that range. You can see in my histogram down here too that I had kind of two different performance ranges for it. There was one range that was 392 to 401, and then one that was 401 to 414, but it's figured out this confidence interval. And the error column is just showing a plus or minus to your mean that represents this range. So 401 minus the 5 gives you 396, and 401 plus the 5 gives you 406. So it's just telling you what that range is. And a lot of times people will see the numbers out of this and they will conclude that because one number is lower than the other one, that's the winner, without really accounting for the error. If they are within range of each other, such that their confidence intervals overlap some, then basically the only thing we can conclude is that the one may be faster than the other one, but they may be the same. So in order to make a definitive call that this one is faster, we need to see that the confidence interval is actually fully below the confidence interval of the other one. And in this case, it is. So what's going on here? Well, I want to go back over to Sharp Lab, and I want to show you why I said initially that there's no difference between these two. So this is the, in Sharp Lab, the C# view of my code. We call this lowered C#. Essentially what's happening is Roslyn is compiling the code that you write into IL, and then they've got a separate IL decompiler that's decompiling that back to C#. And it doesn't know what your original C# looks like, so it's just creating the simplest representation of your code that it can. And I've put together here a for each loop and a for loop looping over a list of T, list event. And what you can see is my for loop here, my for loop has been translated to a while loop, which, ultimately for loop, while loop, do loop, they're all basically the same thing. So that's what it translated to in the lowered C# it's a loop, just like I wrote. The for each loop, on the other hand, looks quite a bit different than the for loop. It is calling get enumerator on that because it is an IEnumerable. So it's fetching the enumerator for it. It set up this try finally because the enumerator is disposable, and it's calling dispose like you're supposed to for things that are disposable. And then it's got a while loop inside, and it's calling move next and current. So obviously this is very different. And this is why I might have thought initially that there could be a performance difference between the for each loop and the for loop, because they have different mechanics in the standard setup for each, the standard mechanism by which for each works. But let me show you what happens if I change this to a span. We make a new overload that accepts a span event, and pop back over here. Here's this method. Look, it's just a regular while loop fetching by index, just like the other one was. Let me change this one to span so we can see that they're actually not different at all. That's going to be length instead of count. So here we go. The for each loop over a span is exactly the same thing as the for loop over the span. Actually, there's one very subtle difference, which is that it's created a temporary variable in the for each version. Remember when we saw the assembly code for this, there was a subtle difference between the two assembly language versions of this, just the order of the first two. That comes down to that extra temp variable that was created here. It's still the same code. But anyway, the C# compiler, when you use a for each loop over an array-like type, and that would be an array or something that looks like an array, like a span, it lowers it to a for loop instead of using this get enumerator and move next and current pattern. And that's why I said that those were the same thing and that they should perform the same. And that my initial question, which is faster, was a silly question. And so this highlights one of the pitfalls of using a benchmark to answer a question that maybe you don't really understand what you're asking. I'm going to go ahead and introduce one more feature of BenchmarkDotNet real quick, which is the params attribute, because this allows me to pass in different values for this property, whatever this property is. I've got it defaulted to 1 mega values. So let's put in an alternative. Let's send in 10 or 1 kilo values, and let's do 16 or 64 kilovalues. So 2 to the 16th. Now, if I do this, I'm not going to run this benchmark because I ran it already, but let me show you what the results look like for that. So for 1024 values, you can see here, I got 361 and 349. Again, looking at the error interval, we can see that these are statistically significant differences. The for loop is showing up as being faster. And we can see for the slightly larger one that it's also statistically significant, but the difference is bigger. And this is kind of a curious thing. So for a smaller length span, we see a difference, but it's pretty small. As the span gets bigger, the difference is getting bigger. So why would that be? If we understand that the question we asked was flawed to begin with, but we're seeing a result like this, we're seeing some other side effect that obviously is not represented in our code. But just in case we wonder whether it was represented in our code, I'm going to use another tool that's available in BenchmarkDotNet, which is the disassembly diagnoser. So if you put this disassembly diagnoser attribute on your benchmark class, then when BenchmarkDotNet builds it, runs it, it will dump out the JIT disassembly version of your code so that you can look at it. I actually meant to do this in advance and I didn't do it, so we're going to have to do it now. Because I'm going to do that now, I'm going to use another advanced feature of the simple job attribute, and that is to set the warm-up count to a small number and the target count to a small number, so this benchmark doesn't run for very long. And the reason I'm doing that is because I don't care what the outcome of this is so much. I just want to get that disassembly. And hopefully I'm not going to mess up my audio again when this runs. This is the first time running with the disassembly diagnoser, so it's got to set up some extra stuff. Oh boy. Well, that's not good. Huh. That was weird. Oh. Okay. There we go. So it's building. I'm gonna wait that out for a second. You notice here it says it's running 4 benchmarks in total, and that's because it's running the 2 benchmarks that I made times 2 values for that params for the span length. You notice they're going by really quickly now because I'm only doing 1 warm up and 1 actual execution. And here we go. A little bit of a clue here. We've got our code size. You can see one's 322 bytes and one's 323 bytes. So this is really backing up what I saw in SharpLab, which is that the for loop and the for each loop are the same thing and they generate the same code. It's the same size. Now I can go grab the actual emitted assembly. When you run a BenchmarkDotNet benchmark, it'll put out a folder. In this case, it's going to be under bin release, net7, BenchmarkDotNet artifacts. And all the spew that went by on the screen goes into these log files, so we can retrieve them later. But in this case, because I was using the assembly diagnoser, disassembly diagnoser, I got this ASM markdown file. And it's showing me the emitted ASM for the for each and the emitted ASM for get span, because it did call that, and then the emitted ASM for for. And if I look at the for, you can see, let's see, there's my call to get span, and then here's the inner loop. This is really the part that we care about. It's moving a value into a register, shoveling it around. Here's that XOR, it's XORing the value from the span. It's incrementing a counter, comparing to see if I'm at the end of the loop. If I'm not at the end of the loop, then it's just jumping right back up to here. So only 1, 2, 3, 4, 5, 6 instructions plus the jump. Let's look back at the other one again. Here we go. 1, 2, 3, 4, 5 instructions plus the jump. Again, the core part being the XOR with the value from the span. So this looks the same, and yet I got this wacky result that says that the for is faster than the for each. So by asking the wrong question, really I've put myself in a trap, because the best possible outcome of this is that I get the correct answer, that the benchmark tells me they're the same. I get the same number, I take the error into account, I see that they're within range of each other, and I say, oh, they're the same, there's the answer to my question. But that's the best possible outcome. It is a realistic outcome that you'll get a different answer for the two of these. Now, some of you are undoubtedly calling shenanigans on this, and there are some shenanigans, I will admit, but the shenanigans that I got up to are completely realistic. What I've done to make the for each loop run slower is I misaligned the data. If you're not familiar with that term, basically what happens is when you allocate an array of int, the GC will guarantee that each of those ints is located at a memory address that is evenly divisible by 4, the size of the int. So we call that natural alignment. Whatever the size of the type is, if it's naturally aligned, the memory address that it's located at will be evenly divisible by the size of that type. For the for loop, I allowed it to use the naturally aligned int array. For the for each loop, I made a copy of the data from that int array, and I stuck it into a byte array that was 1 byte bigger than the original int array and offset by 1 byte. And we can see that in the data class here. So this is my make num array. It's just creating an int array of 1 mega items and then filling them in with random numbers. And then down here to make the byte array, I'm creating a byte array of the same size, numbers.length times the size of it plus 1 byte. And then I'm just copying the data to this other array at an offset of 1 byte. So every single one of those integers is now at an odd memory address. And then here, this is the shenanigans part. In the get span method, I've used caller member name to say that if the caller of this was the for each method, then return it that byte span, just chop off that first offsetting byte and return the actual data. And then anybody else that calls it gets the real span of integers. So that was the shenanigans. And the only difference that I'm enforcing here, again, you saw the code was the same. I just made sure that one of them was working on misaligned data and the other one was working on aligned data. And I want to show you again in the results the kind of impact that can have. When I did a short span, you saw that the difference was smaller than with a big span. And the reason for that is modern processors really aren't too bothered by misaligned data. In general, there's not much of a penalty, but the way your memory cache works in your CPU is that it's organized into 64-byte lines, they call them. And those cache lines are memory aligned. So if I'm reading along a sequence of, a sequence of ints that is sequential in memory, A 64-byte cache line will hold 16 ints. And so when I'm reading 16 ints, I'm just reading right through that cache line. When I hit the end, then I'll move to a different cache line that has the next memory that I'm going to read. The processor will have anticipated that I'm going to keep going, and it will have already loaded that into the cache, and I just keep on cruising 16 ints per cache line, and I'm good. In the for each case where the data is misaligned, I can't read a full 16 out of that cache line. I read 15, and then on the last one, it's missing a byte to fill it in. So I've got to go read that extra byte from the other cache line, merge the two together, and then it can return the int. So it's not much of an impact. It's just a teeny tiny hiccup in reading every 16th value realistically. But it's enough to show up in the benchmark and make it appear as though one of these is faster than the other. And that impact of those cache line splits depends on where you are in the cache hierarchy. In a level 1 cache, that penalty is relatively minor. But when I get into a bigger set of data where it doesn't all fit in the L1 cache and we start reaching into the L2 cache, that penalty becomes bigger. And then when we leave the L2 cache for the L3 cache, it would become bigger. And then when we hit main memory, it becomes even bigger. So, this is the sort of thing that can throw you off in a benchmark where the code is the same. You structured the benchmark correctly. The design of the benchmark is well thought out, but you just get a result that doesn't make sense. And because the question that you asked indicated that you didn't fully understand the problem, you could be led down the wrong path. And in investigating the problem, I actually ended up answering the question anyway, which is kind of which kind of tells you that the benchmark was really the wrong tool for the job in the first place. If I get rid of that memory misalignment and rerun the benchmark, which I did, then we get a better answer, which is yes, they are the same. In this case, the for loop went out by just a teeny tiny amount here, but again, accounting for the confidence interval, we can see that if we added 78 milliseconds to this, subtracted 76 from this, they very much overlap, so we can conclude that they are likely the same. So that's a good example where it could trick you. I'm going to move on to a second example here, another example where we're going to see a bad or an inaccurate result. And what I've done here is I've set up the memory diagnoser, which is one that you've probably seen as well. I'm going to get rid of this invocation count. That was actually the fix. So just like the other one, I've set up a simple job with a low warm-up count and a low target count. I'm going to go over in just a minute how BenchmarkDotNet runs and what these numbers mean. But I set these low because I didn't want it to take forever. And I'm actually not concerned about measuring the speed of these methods, because if you look at them, they're all doing a bunch of sleeps. So they're obviously going to take the time of however long I'm sleeping. But I've added the memory diagnoser attribute, which tells BenchmarkDotNet to give me memory information for this benchmark. And I've got 3 methods here: allocate fast, allocate medium, and allocate slow. They all call gc.allocate_uninitialized_array, passing an account that's taken from this field. So again, if I wanted to use a params attribute to pass in different array lengths and see how those compare, I could do that. And then each one sleeps for a different amount of time. I'm sleeping for 10 milliseconds, 100 milliseconds, and 1,000 milliseconds. And if I look at the results of this benchmark, we will see a couple of new columns. We see the allocated column, and it is accurately telling me that I allocated 1 megabyte per run. That's great. The Gen 0, Gen 1, and Gen 2 columns are also new. This is trying to tell me how many garbage collections will be directly caused by the code I'm running in my benchmark. And down here in the legend, it tells me it's the count of generation 0, 1, or 2 collections per 1,000 operations. So what this is telling me is every 1,000 times I run allocate fast, each one allocating 1 megabyte, by the way, Every 1,000 times I run it, I'm going to get 328 Gen 2 collections. Now, of course, the Gen 2 collection includes Gen 1 and Gen 0, so those are showing the same number. It's telling me on the allocate medium method, for every 1,000 times I run it, I'm going to get 200 collections. And for the allocate slow, for every 1,000 times I run that, I'll have 0 collections. Now, how does that make any sense at all? These are all the same, they're all doing the exact same amount of allocations. So where did these numbers come from? Well, let's go back to answer that question through all of this spew and talk about how BenchmarkDotNet works. There's actually a good page in the documentation for BenchmarkDotNet. This will require some zoom. It is in the guides, it's labeled how it works, and they've kind of written out in pseudocode how BenchmarkDotNet is built. And really what it's going to do is it's going to take the tool chain associated with your job. The simple job that we've been using uses the .NET SDK tool chain associated with whatever with whatever runtime version your benchmark project is targeting. So since I target .NET 7, it's using just the .NET 7 SDK. You can build custom jobs that use other tool chains if you want to use, for example, if I'm running my program x64 and I want to use the x86 tool chain to build an x86 build of something, or if I want to use an older tool chain to generate a .NET framework program or something like that, I can do those things by changing the tool chain in my job. But the overall structure of what it does is it starts by trying to figure out an unroll factor. And it does this because if you think about how to accurately time a method, and let's go back to this method. Program. Go back to this method as an example. This method is doing very, very little work, and it's doing so little work that the overhead of calling the method itself might end up dominating. Maybe this one isn't a great example because it's even calling another method and whatever, but if I were to write a very, very small benchmark, like try to benchmark adding 2 numbers together, for example, it's going to be impossible to measure the add because the overhead of the call itself is going to be greater than the actual action I'm trying to measure. So what BenchmarkDotNet does is it unrolls your method into a larger method, calling it several times in a row. So the unroll factor is how many times it's going to call your method per test that it runs. And by default, it starts out with trying your method 16 times unrolled in that test method. The next thing it's going to do is time your method with that unroll factor and try to figure out how long, if I unroll it by 6, how long does it take one invocation of this to run? And then how many invocations should I run to get a representative sample of the timing of this benchmark? And the heuristic that BenchmarkDotNet uses is it tries to figure out a way to run your thing so that it takes around half a second. They figured out through experience and experimentation that around half a second is a good amount of sampling to get an accurate measurement of how fast your thing is. If it takes longer than that, that's okay, but obviously you don't want to wait forever to get your results. So half a second is kind of that target that it's looking for. And it's figuring out the invocation count based on that. So if it unrolls by 16, how many times would I need to run the test method to get it up to about half a second of runtime? The next thing it does is it figures out what's the overhead of just calling your method. So if you have a method that's got like 15 arguments passed to it, that's going to involve like writing some of those arguments out to the stack and then reading the arguments back from the stack inside the method. So it could have some overhead associated with it. Same thing if you're returning a large value on the stack, that might have some overhead. So it sets up a method that looks just like your method, but has the body stripped out so that they can measure the overhead of the method call itself. So they set up an empty method that looks just like yours, same number of unrolls, same number of invocations, and it it runs through that method to warm it up, get it jitted, get it promoted to tier 1 JIT, all the things that you would need to think about to get accurate measurements, but that you don't need to think about because it does it for you. It's doing all of those things. And then it runs that empty method to get accurate timings on it. Then it runs your method in both a warm-up phase and an actual phase. The number of times is determined by BenchmarkDotNet. By default, it'll do 6 warm-ups and 15 actual iterations. And then it goes through its cleanup. And then they've got broken down, basically what each of these sections does. But I want to show you the very last one, which is the measure GC stats, because this is where the memory diagnoser gets its information. And you can see in the pseudocode here, it says it calls gcstats.readInitial. And in a for loop, for the invoke count divided by the unroll factor, it will call your method this many times, and then it just calls gcstats.readFinal, takes the difference between the two, and that's what it reports. So taking into account all the stuff I just said about how it works and what the invocation counts and iteration counts and unroll factors and all that mean, let's go back and reevaluate what we learned from the membench results. So again, here are all the phases listed as it runs through. You can see here this overhead jitting, that's jitting the empty method. Workload jitting is jitting your real method. Here's where it's trying to figure out how many invocations it wants to run. Again, we've got iterations, invocations, and unrolls. The unroll says how many times your method is called within the test method. Invocations is actually this number that you see right here next to op. So 16 op, 64 op. This is it trying to figure out how many invocations to run to hit that 500 millisecond target. And you can see what it did here is it tried 16, it tried 32, it tried 64. This one took a quarter second. This one took just under half a second. This one took almost 1 second. And it decided, 32 is not quite enough, so I'm going to do 64. And then it did enough warm-ups to make sure that we got consistent results during the warm-up. This is warming up your caches, making sure that the method is truly promoted to tier 1, getting everything under ideal circumstances to measure your method. And then here's where it actually runs. Again, by default, it would run for 15 times. This one had some inconsistent timings. You'll notice it was almost 8 nanoseconds here, or sorry, 400 nanoseconds here, 300 here, various different timings. So it ran more than that. This is actually this looks like it's the overhead. Oh, it says right there, overhead. So this is the empty method, which is why the timings are so low. And then it does the same thing for your real method. So in this case, I set explicitly the warm-up count to 2 and the target count to 5. So it did exactly that. It ran my warm-up twice, ran my actual workload 5 times. And then down here, you can see where it collected its GC stats. And these are the GC counts right here. It observed when executing my method 64 times, it observed 21 garbage collections of Gen 2, which again includes the other generations. And so that ratio, about a third, is what it observed. And if we look at the next one in line that took longer, so this method, because it was taking 100 milliseconds to hit that target time of half a second, it only ran 5 operations. And here's the actual timing for it, 544 milliseconds for the total package. And in that 5 operations, it observed 1 garbage collection. So 1/5 of the time. And finally, down here on the longest one, we were down to 1 operation, because obviously we were already over that half-second limit. It's a full second, so it decided I'm only going to run this 1 time. During that 1 time, it observed 0 garbage collections, and so it is extrapolating the report that it gives you here per 1,000 from the number it actually did run. So if your methods are long running, then this number is extrapolated from a very small sample size and could be completely unrealistic. In fact, for the allocate slow, there are two choices. It either did or did not observe a garbage collection. So the only two possible counts I can get here are 0 or 1,000. So pay special attention to that. Now, there is a way that you can, and this is particularly important when you're measuring things that have wildly different performance characteristics. If I'm actually trying to compare these three methods because they work differently, and let's say memory allocations and GCs are the metric that is most important to me. I don't really care which one is fastest, but I want the one that's the lightest on the GC for some reason or another. If I want to be able to compare these numbers, I absolutely have to get the same number of invocations in order for the numbers to be at all comparable. So in order to do that, I would go up here to the job parameters, and I would set an invocation count. And if I set that to something that's going to take a reasonable amount of time, like 16, and run that benchmark again, then the results that we get, you'll see, because I said 16, I'm getting 16 every time. Out of 16, it observed 5 garbage collections on this one. We go down to the next one, same thing, 16. And look, same number of garbage collections for those 16 operations. And that means at the end, when I get my results, they're all the same. 312 observed per 1,000, of course, extrapolated from 5 out of 16. So be careful about using or especially interpreting these GC count numbers from things that have wildly different times, and pay particular attention to the operation counts because they are dumped right to the screen as they're scrolling by. Watch those. The last thing I want to show you is a kind of a take on if you watched the presentation yesterday from a bunch of Z's, he had a good benchmark in there where he showed array list compared to list and showed just how horribly wasteful and expensive array list is compared to list. But I thought that made kind of an interesting talking point because he specifically was highlighting really the worst case use of array list. And if I didn't know any better, if I were watching that presentation and I saw that and I said, wow, that array list just is truly awful. And I've seen that all over in the code base of my project. I bet you if I went and ripped out all those array lists, suddenly my app would be using, half as much memory and would run twice as fast and the world would be great. So I'm going to go do that. But taking a conclusion about all usage from a single benchmark is not a good idea, because that benchmark is really only answering the one question it was meant to ask. This one, again, was meant to show a really nasty case for array list so that we would understand how it's awful. But that doesn't mean it's always awful. And if you make decisions based on that, that would be unideal. So I've got a benchmark here that is similar, not all the same, but similar to the one that you might have seen yesterday, set up sort of the same way as the ones I did earlier, where I've got a count. I've got this set to 64 kilo items, and I'm just setting up a list event, generic list event versus an array list. I'm adding a constant int just a bunch of times to it, right up to its capacity. And then again, it's not a problem in this case, but I'm returning something from this method just to make sure there's an observable output from it. And again, same thing for the array list, but now I've built the same thing with a string list and an array list in which I have inserted strings. And I'm using a constant int and a constant string in this case, because I don't want to measure anything that I'm not trying to measure. I don't want to measure a bunch of string allocations. So I'm not going to do like i.toString, because now I'm measuring the cost of the list plus the cost of allocating and creating all of those strings. So again, this goes back to making sure that you're only measuring the one thing that you care about measuring. And here are the results of that benchmark. And you can see, much like you saw yesterday, if you watched that presentation, that if we're storing integers, that a generic list of t of int is much more efficient, time efficient, CPU efficient, and much more memory efficient than array list. But we see that with strings, it's the same. They're basically the same. The allocations are exactly the same. The garbage collections are exactly the same. The timing is just a little bit better for list of string versus array list. I can only assume that, you know, the generic list has gotten some performance improvements over the years while they're basically letting array list rot. So it's a little bit slower. But if I drew the conclusion that I should go into my projects and rip out array list and replace it with list of T, and what I was storing in my array list was nothing but objects, strings, then I'm actually not going to see any benefit from that at all. So make sure you're measuring the thing that you meant to measure. I do want to talk about, since I showed you an example where the allocations can be inaccurate, I wanted to show you just how accurate they can be when you're measuring something where that's kind of important for you to know. So let's think about what this allocation means. So 256K was allocated for the int collection, and that's because I was doing 65,536 or 64K items times, these are ints, so times 4. So 65 times 4 is 256. So that's what we saw in the allocations, 256K. That's great. That's what we're showing, is that the list of int is backed by an array of int. So that's how much each item takes. That's how many items there are. That's how much we got. A list of string is going to be twice as big because the backing array is going to be an array of string. String is a reference type. I'm running a 64-bit program here, so each reference is 64 bits, 8 bytes. So it comes out twice as much memory because the backing array itself is twice as big. And for array list of string, it's exactly the same. The array list is backed by an array of object. All references are the same size, 8 bytes. So it doesn't matter what type of object I'm putting in there, they're all going to be the same size. They take up the same space, so there's no extra cost there. But the array list, if we're storing value types in there, value types have to be, you can't store a value in a reference type array, so they have to be boxed. And the cost of boxing that thing, I wanted to show you in SharpLab in case you haven't seen this. This came up in chat the other day. There's a nice tool in SharpLab, which is a memory inspector that lets you see what the layout of an object is in memory. And I've got 3 classes here: one an empty class, no fields, one class that has an int in it, and one class that has 3 ints in it. And I've just run this inspect.heap against new instances of those classes. And I wish I could rearrange these panes. Don't like that, but anyway, what we see here is that for each of these objects, there's an 8-byte header. We've got an 8-byte type handle, which is actually just a pointer to the method table for that type. And then we've got an area for some data. The empty class has an area for 8 bytes of data, even though it doesn't have any data at all. The int one is using the first 4 bytes of that data area for the int. And then the one with 3 ints has filled up that 8 bytes of extra space and then taken an extra 4 bytes for the third field, and then another 4 bytes of padding because objects need to be padded out to increments of 8 bytes. A couple of interesting things we can see here. This is kind of a fun one. Well, first of all, let me just show you. If I were to stick a value type onto the heap, and I can just throw an int in there like this. This is running right now, so give it a second. Here we go. Now we see what a boxed object looks like. It says here I've got an object of type system.int32. That's a boxed int32, and same deal. It's got an object header, it's got a type handle, and then it's got that data area where m_value represents the boxed int, and there's that 42 sitting in memory. So this is so we can see the cost of boxing just a single integer. If we box a 4-byte integer, it actually takes 24 bytes in memory to box that. So let's go back to these stats and add that up. So if I do calculator, let's do 24 bytes times 64 K items. This is measuring in K, so I'm just going to leave the K part off. So it's 1536 plus the 512.11 for the overhead of the list itself and the object array that backs it. And boom, 2048.11, the exact amount allocated. So we see the exact cost of all those boxed ints in those stats. So that's really nice. And actually, I hit the time exactly on this, so I'm going to go ahead and stop there. I guess I'll leave this kind of idling here. I'm going to check Discord on my phone and see what we have for questions, if any. Let's see here. Okay, I got a question. If I didn't say this already, is there a way to integrate BenchmarkDotNet with tests for my library so I could run tests every time I open the console project, every time I want to see the results? So the way that I set it up is probably the easiest way to do this. BenchmarkDotNet by its nature has to generate its own program and strip out those benchmark marked classes. So you can kind of harness it into anything you want. That benchmark runner is actually what triggers all of that to happen. So you can integrate it into any other type of program. The way I did that first one is kind of typical of how I do it. So I'll set up, I'll set up a baseline method that does a thing that I would like to improve the performance of, and I'll put, a return value that's sort of that dummy check to make sure I got the right answer, and then I will create alternative implementations of it, trying to get a faster one, and then I'll run it just like I did here. Run the program, kind of dump the dummy check values out to the console, and then if those are good, just have some way to trigger running the benchmarks on top of it. I wouldn't try to integrate it into an actual unit test project or anything like that, but it does integrate cleanly into any type of project. Let's see, what was the most interesting, surprising result you've observed while running a benchmark? I don't know, it's hard to say most interesting, but the examples that I've shown here are kind of among the most interesting types of examples where some external factor like data alignment or code alignment causes you to see a difference that isn't there. Or I can think of one example that came up on the C# Discord. We were trying to help somebody optimize this really complex function, and the function was designed such that there was a simple case for it and a complex case for it, and the simple case just did a simple calculation and could return quickly. The complex case was very complex, took a long time. So we were helping him speed that up. And the answer that we gave him was, well, if you do the complex case as a lookup table, then that will make that part fast too. And he did it, and he had a benchmark, and he was running it over and over again. And it kept saying that the lookup table wasn't any faster. And it turned out we all banged our heads against this for several minutes before having the duh moment. Wait a minute, what data are you passing into this? It turned out he was passing in an array of all zeros, and so he was always hitting the simple case, so he never got to see how expensive the expensive part was, and he never got to see the advantage of the cheap part. So pay attention to your data as well. Let's see, from YouTube, can we use it with async await function like with web APIs? Yes, you can. In fact, I would recommend highly watching Mike Trait's presentation from yesterday about async, because he does a bunch of benchmarks in there doing exactly that, and has some good pointers in there. Could it be possible that different compilers break for each down in a different way that it could be heavier? Yes, it could be. I don't know why at this point in time you would use a different compiler than Roslyn, but that is kind of a trick that it knows. For array-like types, turn it into a while loop is cheaper. That's something that's coded into Roslyn. So if you had some, I don't know, some other C# compiler you were using, it could use the get enumerator and move next current pattern, because span does implement those things. It wouldn't necessarily be any slower to do it that way because that stuff is highly optimized, but it could cause it to run differently. Let's see. Can I make any form of clarification about running benchmark.net on CI, especially a public agent pool? Do you try to make correlation to see how bad it goes? I have never actually tried that. I might ask, I don't know if Sergio does that, so you might ask in the allow unsafe blocks channel. I don't run benchmarks in CI just because you really need to have predictable hardware in order to get meaningful, predictable results. And CI environments, especially the free ones that we get with open source, you never know what you're going to get, so you're not necessarily going to be able to meaningfully compare run against run over time. You might be able to do a comparison on an environment that you don't have access to. Like if I wanted to benchmark something on Mac and I don't have a Mac, I might be able to set that up and run something, but it would be highly dependent on the CI environment itself. What other resources beside this great talk? Ooh, that was nice. Sorry, I just went to sleep. Can you recommend to people to want to learn more about benchmarks? Well, the documentation, I will say, from on benchmarkdotnet.org is really excellent. And the samples in particular are great. They've got, benchmark.net just has a ton of cool features that I didn't have time to go into. But one of my favorite features that it has is you can use it to run for NuGet packages. You can create yourself a job and then add different jobs that build your program bound against different versions of NuGet packages. And I use this with my own NuGet packages to trace or to make sure I catch regressions, if any, or to show improvements version over version with this kind of a setup. So these samples are just are excellent, and they have all kinds of advanced scenarios that I didn't have time to get into. Regarding OS clock resolution, there was a topic lastly about thread.sleep, task.delay, datetime.now. Any clarification about why you shouldn't expect anything below the clock precision, because I mentioned stopwatch. So yeah, that's a good question. One of the things you'll see actually, if you were to write a dumb benchmark that doesn't use benchmark.net and is doing everything as wrong as you possibly could, and you used benchmark and you used datetime.now as your timer, what you would find is that the resolution of datetime.now is around 15, 16 milliseconds, because that's the standard time slice in Windows. The stopwatch class in .NET uses the Windows performance counters that are tied directly into the hardware clock in your CPU. So so that is the highest resolution timer that you're going to have access to in .NET. And if you query the stopwatch class, there's a property on it called timer frequency, and that will actually tell you how many ticks per millisecond, or I guess it's better expressed the other way around, how many nanoseconds per tick your specific clock is. But that is the highest resolution timer, so absolutely use that for measuring anything that you care about precision, because all those other things that are timer based are going to be limited to the Windows time slice clock, which again by default is 15, 16 milliseconds, but it's possible for other things in the system to change it, so that number could actually be a lot higher. Do I know what kind of existing stack to pull out of how to sort of cluster a predictable VM like Tech and Power, Job Dispatch? Let's see. Yeah, so so that's a setup where Microsoft has their own dedicated hardware to that stuff. I haven't seen a good tool for extracting all of that stuff and building reports out of it. I don't know how much of Microsoft's infrastructure is open source either. That I would ask also in the allow unsafe blocks channel, because Jaeger probably can tell you what the setup is at Microsoft, because he uses it all the time. Are there any alternatives to BDN? What's my standpoint on them? Is BDN the standard? There is nothing like BDN. It is the tool for benchmarking. One thing I will say is that benchmark.net is a micro benchmark tool, and I didn't talk about that, but a micro benchmark ideally is something that takes in the neighborhood of, let's say 100 nanoseconds to 100 milliseconds, which that's a pretty broad range, but it doesn't cover everything. Certainly we want to be able to measure the performance of things that take longer than 100 milliseconds or a second or whatever. But you saw what happened in that memory example, where if you have a benchmark method that takes a full second or any amount of time more than half a second, BDN will only run it once. So a lot of the mechanics in BDN that go into giving you accurate results start to fall apart when you're doing a longer benchmark. So in that case, if you have a test that takes 5 seconds or 15 seconds to run, falling back to a stopwatch timer for those things, there is no shame in doing that. You do probably want to do multiple runs of it and average them just to make sure you get a good statistically valid sampling. But definitely use BDN if you're doing micro benchmarks. One other thing I wanted to mention that I didn't talk about was I said that my timer resolution is 100 nanoseconds on my machine. So how would BenchmarkDotNet tell you that you've got a method that takes 5 nanoseconds, for example, or even less than that? And the answer comes back to that unroll factor. So if it unrolls your method 100 times and then runs it a bunch of invocations, and it'll get up into the millions. If it runs it 1,000,000 times and then measures that whole thing at 500 milliseconds, then it can come back and say, this took 5 nanoseconds to run just by dividing the total time by the total number of times it ran. So it's interpolating that result, but it's doing a really good job of getting it accurate, even though you couldn't technically measure any distance of time that short. What's the status of Crankier? And it's still exactly what does it give on top of other tools? I haven't used Crankier. I know the performance repo in .NET uses Crank, and that's what they generate their Power BI reports out of, but it's not one that I've used. Let's see. I think that's all the questions I see. We got some typing, but I think that might be it. Oh yeah, we got a person typing, so we'll see what that is. Grab a drink real quick. Too late. What's the most difficult benchmark I've concluded? I would say any of those that involve like data alignment or code alignment, it can be really tricky, especially when you get into SIMD. The example that I used was integers, and in realistic cases, you'll never see misaligned integers, so that's probably not a scenario that you'll run into, but you will run into it with SIMD, because in SIMD, we're reading chunks of data, 16 bytes or 32 bytes at a time. And when we get access to AVX 512, it'll be 64 bytes at a time. So think about, I said with integer data types, you may hit a cache line split every 16 values, but with SIMD, you may hit a cache line split every 4 values or every 2 values. And those kinds of, alignment dependent or environment dependent differences that show up can be really, really tricky to measure, especially when you're trying to get down to, which is faster, executing this unrolled by 2 or unrolled by 3, and those things. So I wouldn't say it's necessarily difficult, but it is tedious to get the right answer. But and this is one of the core parts of benchmark is that you have to come up with a good design, but you also have to put in the effort and the time to actually get good results out of it, because it spits out a number, but that number is answering a question that might not be the right one. Let's see, anything worth noting if there are differences between the GC gens? Yeah, absolutely. So GC gens, Gen 2, I was showing you a bunch of Gen 2 collections because specifically I was doing large allocations. I was allocating 1 megabyte at a time. When you do small allocations, there's different things that can trigger a GC. One of the things that triggers a GC is that you ask the GC for some memory and it doesn't have any because you've already used up all the memory that it pre-allocated for you. I wanted to touch on this and I didn't get time to, but The reason that we care about allocations in general is that allocations of memory do not show up in the timings of your method. In fact, if a GC were to kick in during the run of one of your benchmark methods, it'll make it take longer, and BDN will actually intentionally throw it out because it's an outlier. So when we see that timing on your method, that does not include the overhead of memory management, but that overhead exists, and it will be paid not just by your method, but by anything else running in the system at the time. And Gen 0 collections are fast and cheap. Gen 1 is slower and more expensive. Gen 2 is a very expensive collection. So those GC counts and the allocation count is giving you an idea of the latent cost of garbage that isn't showing up in your timings, but is very important. So that's, I guess, all we have time to say about that. So I guess that wraps us up. And thanks everybody for joining, and enjoy the rest of the conference.